What if you could step into a machine and visit any point in time? Imagine the possibilities, witnessing the construction of the pyramids, sitting in on Da Vinci's creative moments, or even exploring the future to see humanity's greatest achievements. Time travel has captivated our imaginations for generations, fueled by iconic works of fiction like Back to the Future, where a souped-up DeLorean takes its passengers on thrilling journeys, or Interstellar, where time itself bends around the pull of a black hole. These stories aren't just entertainment, they touch on a deep human longing to understand time and possibly rewrite it. Why are we so fascinated by the idea of time travel? Perhaps it's our innate curiosity about what lies beyond our present reality. Time is a mysterious force, one we experience constantly yet barely understand. For some, it's the ultimate tool for redemption, a way to undo mistakes or alter the course of history. For others, it's a scientific puzzle waiting to be solved. Time travel doesn't just challenge the boundaries of physics, it forces us to grapple with profound philosophical, ethical, and societal questions. If it became possible, would we use it responsibly, or would we disrupt the fragile balance of the past and future? In this video, we'll dive deep into the science behind time travel, exploring the theories and breakthroughs that suggest it might not be entirely out of reach. From Einstein's groundbreaking theory of relativity to the tantalizing possibilities of wormholes and quantum mechanics, the pursuit of time travel is a story of human ingenuity and relentless curiosity. We'll also look at historical attempts to understand time and how these ideas evolved from myths to scientific hypotheses. Along the way, we'll uncover some of the most intriguing breakthroughs, like experiments that hint at the possibility of time dilation and time loops. But it's not all smooth sailing. Time travel presents significant challenges, from the staggering energy requirements to the paradoxes that defy logic, like the infamous grandfather paradox. As we navigate the controversies and ethical dilemmas surrounding time travel, we'll consider how close humanity really is to making it a reality. Are there scientists today actively working on this concept? What might their findings mean for the future of science and society? This exploration doesn't just examine the cutting edge of physics, it paints a vision of what time travel could mean for humanity's future. By the end of this journey, you'll have a deeper understanding of one of science's most tantalizing frontiers. So, how close are we to discovering time travel? Stay tuned as we unravel the mysteries, the possibilities, and the extraordinary challenges of bending the fabric of time itself. The concept of time travel in science fiction and human imagination. And why time travel resonates. The allure of time travel stems from a profound human yearning, the desire to undo past mistakes or peer into the future. Imagine being able to erase a moment of regret, relive the happiest days of your life, or even witness the unimaginable advancements of a distant tomorrow. This idea touches a universal chord, the hope that we might control time, a force that so often feels beyond our grasp. Throughout history, time travel has been a recurring theme in literature, folklore, and storytelling. Ancient myths from various cultures hinted at the concept of bending or traversing time. In Hindu mythology, the Mahabharata describes King Kakudmi traveling to meet the god Brahma, only to find that lifetimes had passed on Earth in his absence. a narrative strikingly similar to modern theories of time dilation. One of the earliest and most iconic representations of time travel in literature is H.G. Wells' The Time Machine, 1895. Wells not only envisioned a machine that could traverse time but also used the story to explore themes of human evolution and societal decay. This groundbreaking novel set the foundation for countless other works, inspiring readers to imagine the mechanics of time travel and the consequences of manipulating time. In cinema, time travel continues to capture imaginations. Films like Back to the Future brought the idea to mainstream audiences, presenting it as a thrilling adventure while delving into the complexities of altering timelines. Similarly, Interstellar took a more scientific approach, showing how gravitational time dilation could make time slow down near a black hole. Even Doctor Who, with its whimsical portrayal of time travel via the TARDIS, has profoundly shaped popular culture's understanding of this concept. These stories resonate because they tap into fundamental questions about our existence. What would you do differently if you could change the past? How would humanity evolve if we could see the future? Time travel allows us to dream about possibilities that extend far beyond the limits of our reality. Science fiction's influence on science. The boundary between science fiction and science fact is often blurrier than we realize. Many of the world's greatest scientific advancements began as imaginative ideas, and time travel is no exception. Writers like H.G. Wells and Isaac Asimov didn't just entertain, they inspired generations of scientists to explore the physics behind their stories. Albert Einstein's theory of relativity, a cornerstone of modern physics, is one such example of how fiction can influence science. In relativity, time isn't a constant. It's a dimension, just like space, and it can stretch or compress under certain conditions. This revolutionary idea opened the door to serious discussions about the feasibility of time travel. Science fiction laid the groundwork by popularizing the notion, making complex concepts accessible to the public. Even today, scientists credit speculative fiction for igniting their curiosity. Kip Thorne, a Nobel Prize-winning physicist, acknowledges that his work on wormholes, a potential mechanism for time travel, was partially inspired by science fiction. In turn, his theories have influenced films like Interstellar, which brought the nuances of relativistic physics to a global audience. Science fiction serves as a testing ground for ideas, allowing writers and thinkers to explore concepts that might initially seem impossible. Over time, these ideas often spark genuine scientific inquiry. The concept of wormholes, for instance, was initially considered a speculative solution to Einstein's equations. Now, researchers explore their potential not only as shortcuts through space but also as theoretical portals through time. By encouraging scientific curiosity, science fiction has played a pivotal role in shaping the trajectory of time travel research. It has allowed humanity to think beyond current limitations and imagine what might be achievable in the future. Cultural impact. Time travel isn't just a scientific or literary fascination, it's a cultural phenomenon that shapes how we think about history, the future, and our place in the universe. The concept challenges linear perceptions of time, forcing us to reconsider what we know about causality, destiny, and free will. In many ways, time travel offers a unique lens through which we examine history. Stories of time travel often involve revisiting pivotal moments, attempting to prevent catastrophes or witness historical milestones firsthand. This speculative approach helps us appreciate the weight of historical events and consider how small changes could ripple across time. Culturally, time travel also fuels discussions about the future. By imagining scenarios in which humanity advances or regresses, time travel narratives encourage reflection on the choices we make today. Movies like Looper or The Terminator explore dystopian futures, cautioning us about the potential consequences of our actions, while others, like Bill and Ted's Excellent Adventure, emphasize the possibility of learning and growing through time travel adventures. Time travel stories often raise questions about personal identity and the human condition. For instance, if you could meet a younger version of yourself, what would you say? If you saw your future, would it motivate you or fill you with dread? These narratives resonate deeply because they reflect universal experiences of growth, regret, and hope. Beyond fiction, time travel has become a metaphor for how we view our lives. Phrases like living in the moment or learning from the past embody the philosophical dimensions of time. The concept of revisiting the past or glimpsing the future inspires people to reflect on their choices and consider the broader implications of their actions. Even in educational and scientific contexts, time travel has an enduring influence. It's a topic that bridges disciplines, engaging physicists, philosophers, and storytellers alike. Schools use time travel as a tool to teach history, while scientists use it to explain complex theories in relatable ways. The result is a shared cultural fascination that transcends boundaries, making time travel one of the most universally compelling ideas in human imagination. Time travel is more than a fantasy. It's a framework for exploring some of the most profound questions about existence. Why are we here? How does the past shape the present? What might the future hold? These questions drive humanity's pursuit of knowledge, ensuring that time travel remains not just a fictional dream but an enduring subject of scientific and cultural inquiry. Scientific foundations of time travel. Time is a dimension. To understand the scientific foundations of time travel, we must first redefine how we perceive time. Traditionally, time has been seen as a constant flow, ticking away uniformly for everyone. However, Albert Einstein's groundbreaking theory of general relativity revolutionized this notion, revealing that time is not a fixed entity but a dimension intricately woven with space. Together, they form what is known as space-time, a four-dimensional fabric where events occur. In Einstein's framework, massive objects like planets and stars warp spacetime, creating curves or dimples. This warping affects the flow of time, making it relative rather than absolute. For example, closer to a massive object, time moves slower relative to regions farther away. This phenomenon, known as gravitational time dilation, has been confirmed through experiments using atomic clocks placed at varying altitudes on Earth. Clocks at higher altitudes, experiencing weaker gravitational pull, tick slightly faster than those closer to the planet's surface. One of the most fascinating implications of relativity is the concept of time dilation at high speeds. When an object approaches the speed of light, time slows down for it relative to an observer. This principle is famously illustrated in the twin paradox. Imagine two twins, one remains on Earth while the other travels on a spaceship near the speed of light. Upon the traveling twins' return, they would be younger than their sibling. This effect, though counterintuitive, has been experimentally validated. For instance, particles called muons, which decay rapidly, last significantly longer when moving at near light speeds, demonstrating time dilation in action. Einstein's theories lay the foundation for understanding time travel within the laws of physics. By manipulating space-time, either by moving at incredible speeds or by navigating areas of intense gravitational fields, time travel in a forward direction becomes scientifically plausible. The challenge lies in figuring out how to achieve this in practice. Could these principles one day allow humans to traverse time? Scientists are still grappling with this question, but the theoretical groundwork is undeniably compelling. Wormholes and black holes. While time dilation offers a way to travel into the future, the concept of traversing the past or creating shortcuts through time requires a different mechanism. Enter wormholes, theoretical passages through space-time that could connect distant points, and potentially different times, in the universe. Originally theorized by Einstein and Nathan Rosen, and later expanded upon by physicist Kip Thorne, wormholes represent one of the most tantalizing ideas in the realm of time travel. Wormholes, also called Einstein-Rosen bridges, can be visualized as tunnels with two ends, each located at different points in space-time. If these points existed in different times, traveling through the wormhole could theoretically allow someone to move from one era to another. However, these structures are highly unstable. The intense energy and exotic matter needed to keep a wormhole open for passage are far beyond our current technological capabilities. Additionally, even if a stable wormhole could be created, questions about causality and paradoxes, such as what happens if you change the past, complicate the feasibility of using them for time travel. Black holes, on the other hand, offer a more tangible, albeit dangerous, connection to time manipulation. These massive celestial objects, formed from the remnants of collapsed stars, create gravitational fields so intense that not even light can escape. Surrounding a black hole is an area called the event horizon, beyond which nothing can return. However, near the event horizon, time behaves in extraordinary ways. As objects approach a black hole, they experience gravitational time dilation, where time slows dramatically compared to regions farther away. In theory, this phenomenon could allow an observer to skip forward in time. For instance, a person orbiting near a black hole could experience mere hours, while years pass for those farther away. This concept, showcased in the film Interstellar, is grounded in real science, based on calculations provided by Kip Thorne. Yet, using black holes for time travel is fraught with challenges. Approaching a black hole risks being pulled into its singularity, a point where space-time curves infinitely and the laws of physics as we know them break down. The intense tidal forces, or spaghettification, would stretch and compress any object beyond recognition. While black holes offer a glimpse into how gravity affects time, harnessing them as tools for controlled time travel remains purely theoretical. Together, wormholes and black holes demonstrate the profound ways in which space-time can be bent and manipulated. They highlight the scientific possibility of time travel while reminding us of the immense challenges involved. Whether through exotic wormholes or the extreme gravitational forces of black holes, these phenomena suggest that time travel, while still theoretical, may not be entirely relegated to the realm of science fiction. The journey to unravel their secrets continues to push the boundaries of human understanding. Quantum mechanics and time travel. While Einstein's theory of relativity provides a foundation for understanding time as a flexible dimension, quantum mechanics offers another avenue for exploring the mysteries of time travel. Quantum mechanics governs the behavior of particles at the smallest scales, and its principles often defy our everyday understanding of reality. One such principle is quantum superposition, which suggests that particles can exist in multiple states simultaneously until measured or observed. This duality raises fascinating questions about the nature of time. One concept derived from quantum mechanics is retrocausality, the idea that the future can influence the past. In certain quantum experiments, particles appear to behave as if decisions made in the present can retroactively affect their earlier states. For example, the delayed choice quantum eraser experiment shows that the behavior of a particle can be determined after it has been observed, as if the particle knows what happens in the future. While retrocausality is not time travel in the traditional sense, it challenges our linear understanding of cause and effect, opening the door to new interpretations of time's flow. Another compelling quantum theory related to time travel is the many worlds interpretation. Proposed by physicist Hugh Everett, this theory suggests that every quantum decision creates a branching universe, resulting in an infinite number of parallel realities. If true, time travel might involve not just moving through time but also transitioning between these parallel worlds. For example, traveling back in time and changing the past wouldn't alter the timeline you came from but would create a new branch where those changes take effect. This could potentially resolve paradoxes like the grandfather paradox, since your actions wouldn't affect the timeline of your original reality. Quantum entanglement also adds a layer of intrigue to the concept of time travel. In entanglement, two particles become so deeply linked that the state of one instantly determines the state of the other, regardless of the distance between them. Some theorists speculate that understanding the mechanisms behind entanglement could unlock ways to transmit information, or even matter, across time. While quantum mechanics provides a wealth of theoretical possibilities, translating these principles into practical time travel remains an enormous challenge. However, the field continues to push the boundaries of what we understand about time, suggesting that the answers might lie not in manipulating the macroscopic space-time continuum, as Einstein envisioned, but in mastering the strange and unpredictable behavior of the quantum world. Case study: Ronald Mallet and the quest for time travel. Among the scientists who have dared to turn the dream of time travel into reality, Ronald Mallet stands out as a pioneer. Ronald Mallet and the quest for time travel. Among the scientists who have dared to turn the dream of time travel into reality, Ronald Mallet stands out as a pioneer. Ronald Mallet stands out as a pioneer. A theoretical physicist and professor emeritus at the University of Connecticut, Mallett has devoted much of his career to exploring the feasibility of time travel. Inspired by personal tragedy, his father's untimely death when Mallett was just 10 years old, he became determined to unlock the secrets of time and potentially find a way to reconnect with the past. Mallett's research builds on Einstein's theory of general relativity, particularly the concept that massive objects can warp space-time. His proposed time machine involves using a circulating beam of laser light to create a rotating space-time region. In theory, this rotating space-time could generate closed time-like curves, CTCs, a phenomenon that might allow particles, or even information, to loop back in time. While Mallett's work has captured the public's imagination, it has also faced significant skepticism from the scientific community. One major criticism is that his time machine design would likely require immense amounts of energy, far beyond what is currently achievable. Additionally, even if the design worked, it would only allow time travel back to the moment the machine was first activated. This limitation means it wouldn't allow visits to points in the distant past or future beyond the machine's operational window. Another challenge lies in the practical application of his ideas. Creating the necessary conditions for rotating space-time on a macroscopic scale would require advances in laser technology and energy generation that are decades, if not centuries, away. Despite these hurdles, Mallett's research has sparked valuable discussions about the plausibility of time travel, blending scientific rigor with a relentless curiosity. Mallett is not alone in his pursuit. Other researchers have explored time travel through different avenues, such as wormholes, quantum mechanics, and advanced computational models. However, Mallett's work stands out for its accessibility to the public, thanks to his ability to explain complex theories in relatable terms. His story illustrates both the promise and the pitfalls of time travel research, a field where imagination and scientific inquiry collide. While the feasibility of time travel remains uncertain, Mallett's contributions highlight the importance of daring to explore the unknown. His work reminds us that even the boldest ideas begin with small steps and that the journey toward understanding time is as much about the questions we ask as the answers we find. Breakthroughs and theories on time travel. Historical attempts at understanding time. The quest to understand time has captivated human civilizations for millennia, with ancient cultures offering rich and varied interpretations of this elusive concept. The Greeks, for instance, envisioned time as cyclical rather than linear. Their mythology depicted Cronus, the god of time, as a force governing the universe in an endless loop of creation and destruction. Philosophers like Plato and Aristotle further debated the nature of time, with Aristotle proposing that time was a measure of change and motion. These ideas, while abstract, laid the groundwork for later scientific inquiry into the mechanics of time. In contrast, the Mayans developed an intricate understanding of time rooted in astronomy and mathematics. Their calendar systems, such as the long count calendar, were designed to track vast spans of time with remarkable precision. For the Mayans, time was sacred, and its cyclical nature was believed to govern the fate of humanity. Their ability to predict celestial events, such as solar eclipses, underscores the sophistication of the temporal observations. Though their focus was more spiritual than scientific, the Mayans' methods demonstrated a profound understanding of time's relationship with the natural world. As the scientific revolution unfolded, thinkers like Isaac Newton brought a transformative perspective to the study of time. Newton introduced the concept of absolute time, viewing it as a universal constant that flowed independently of external forces. In his Principia Mathematica, Newton described time as a river that moved uniformly, unaffected by the motion of objects within it. This notion of absolute time dominated scientific thought for centuries, shaping how humans understood the fabric of reality. However, the 20th century saw a seismic shift with Albert Einstein's theory of relativity. Unlike Newton, Einstein argued that time was not absolute but relative, varying based on an observer's position and velocity. He demonstrated that massive objects could warp space-time, affecting the flow of time itself. This radical departure from Newtonian mechanics fundamentally altered our understanding of time and set the stage for modern theories of time travel. The journey from ancient myths to Einstein's equations reveals humanity's evolving attempts to grasp the nature of time. Whether seen as a divine force, a cyclical rhythm, or a measurable dimension, time has always been a central mystery. These historical efforts highlight the ingenuity and curiosity that continue to drive our exploration of time travel today. Modern breakthroughs. Modern science has taken humanity's understanding of time to unprecedented heights, offering experimental evidence and groundbreaking discoveries that bring time travel closer to plausibility. One of the most compelling demonstrations of time dilation, a cornerstone of Einstein's relativity, came in the 1970s with the Haffler-Keating experiment. In this landmark study, atomic clocks were flown aboard commercial airplanes traveling in opposite directions around the globe. When the clocks were compared to those that remained stationary on the ground, the airborne clocks showed measurable differences in time, consistent with predictions from Einstein's theory. This experiment provided direct evidence that time moves differently for objects in motion compared to those at rest, proving that time is not an immutable constant. In another remarkable test of time dilation, scientists placed highly accurate atomic clocks on the International Space Station, ISS, which orbits Earth at tremendous speeds. The results revealed that astronauts aboard the ISS age slightly slower than people on Earth due to the effects of their velocity on time. These findings demonstrate that time travel into the future is not only theoretically possible but is already being experienced on a microscopic scale. Though the differences are minuscule, mere fractions of a second, they validate the fundamental principles of relativistic time travel. Beyond relativity, advances in particle physics have opened new doors to understanding time at the quantum level. One intriguing breakthrough involves time reversal at the subatomic scale. In certain controlled experiments, researchers have observed particles behaving as if they are moving backward in time. For example, in quantum systems, the behavior of particles can be influenced by future states, a phenomenon often described as time symmetry. While these findings remain largely confined to theoretical and experimental realms, they challenge conventional ideas about the unidirectional flow of time. Another fascinating development in particle physics is the discovery of time crystals, a new phase of matter first observed in 2016. Unlike traditional crystals, which repeat their structure in space, time crystals exhibit patterns that repeat in time. This peculiar property suggests that time crystals could help scientists better understand time's fundamental nature and its relationship with quantum mechanics. Although their practical applications remain speculative, time crystals represent a significant step toward unraveling the mysteries of time. These modern breakthroughs not only confirm aspects of Einstein's theories but also expand our understanding of time into realms he never envisioned. From the precise ticking of atomic clocks to the enigmatic behavior of subatomic particles, science continues to push the boundaries of what we know about time. As experiments grow more sophisticated, the dream of harnessing time for travel, whether forward or backward, feels increasingly within reach. However, the journey is far from over, and the next major discovery may redefine our understanding of time once again. Breakthroughs and theories on time travel, the grandfather paradox and causal loop. One of the most intriguing challenges in the realm of time travel is the concept of paradoxes, which arise from the very idea of altering the timeline. The grandfather paradox is perhaps the most famous example. It posits a scenario where a time traveler goes back in time and prevents their own grandfather from meeting the grandmother. If this were to happen, the time traveler would never have been born, creating a logical inconsistency. The paradox questions the feasibility of changing events in the past without disrupting the causality chain that led to the present. Another puzzling phenomenon is the concept of causal loops, which occur when a future event influences a past event, which in turn causes the future event. For example, imagine a scenario where a time traveler receives a piece of information in the future and then travels to the past to deliver that same information. Where did the information originate? This loop defies the typical cause and effect relationship, creating what some scientists refer to as a closed time-like curve. Such loops challenge our understanding of time and causality, suggesting that time travel might require a re-evaluation of how events are connected. To address these paradoxes, theoretical physicists have proposed potential solutions, one of which is the Novikov self-consistency principle. This principle suggests that any actions taken by a time traveler were always part of history, ensuring that paradoxes cannot occur. In the case of the grandfather paradox, this would mean the time traveler's attempt to prevent their grandfather's marriage would fail because history is immutable. While this principle preserves causality, it also limits the freedom of a time traveler to make meaningful changes. Another potential solution lies in the many worlds interpretation of quantum mechanics, which suggests that every possible outcome of an event spawns a new parallel universe. If a time traveler were to change the past, they would simply create an alternate timeline, leaving their original timeline unaffected. This framework avoids paradoxes by ensuring that changes in one universe do not ripple into others. However, it raises questions about the nature of these alternate timelines and whether they are accessible or observable. These paradoxes highlight the complexity of time travel as a concept, both scientifically and philosophically. They underscore the challenges researchers face in reconciling time travel with the laws of physics and our understanding of causality. While solutions like the Novikov principle and many worlds interpretation offer theoretical frameworks, they remain speculative, leaving the paradoxes of time travel an open and fascinating mystery. Controversial insight. Time travel theories often inspire ideas that push the boundaries of conventional science. Fringe theories, while controversial, offer imaginative possibilities for how time travel might work. One such theory involves tachyons, hypothetical particles that travel faster than light. Tachyons, if they exist, could theoretically move backward in time. Their existence is consistent with Einstein's equations under certain conditions, but no experimental evidence has ever confirmed their presence. Despite this, tachyons remain a staple of time travel discussions, fueling speculation about their role in enabling backward time travel. Another controversial idea involves time crystals, a unique phase of matter that defies traditional laws of thermodynamics. Discovered in 2016, time crystals exhibit repetitive motion in time without consuming energy, making them a potential tool for understanding time on a quantum level. While their connection to time travel remains speculative, time crystals challenge existing frameworks of time and motion, suggesting that our understanding of temporal mechanics is far from complete. Some theorists also explore the possibility of advanced civilizations or entities manipulating time. Hypotheses such as the simulation argument propose that our universe could be a sophisticated simulation, with time as a construct that might be adjustable by those running the system. Though lacking empirical evidence, these ideas provoke philosophical debates about the nature of reality and time's true essence. Another fringe concept is the idea of closed time-like curves, CTCs, a solution to Einstein's field equations. These curves, theoretically created by rotating black holes or exotic matter, could enable time travel by looping spacetime back on itself. However, the energy requirements and stability issues surrounding CTCs make them largely theoretical, with no practical implementation in sight. Critics argue that many of these theories, while mathematically intriguing, are unlikely to ever be testable or applicable in real-world scenarios. Yet, even as fringe theories, they serve an essential role in expanding the boundaries of scientific thought. By questioning established norms and exploring uncharted territory, these ideas keep the pursuit of time travel alive, inspiring new generations of scientists to consider the impossible. The beauty of controversial insights lies in their ability to challenge the status quo. While many of these theories may never progress beyond speculation, they highlight the creative thinking required to tackle one of humanity's most enduring mysteries. Whether through tachyons, time crystals, or simulated realities, these fringe ideas remind us that the quest to understand time travel is as much about imagination as it is about science. Challenges and ethical dilemmas. Scientific hurdle. Despite its allure, time travel remains one of the most challenging concepts to bring from theory into reality, largely due to the immense scientific hurdles it presents. Among the most significant is the staggering energy requirement. Theoretical physicists have long suggested that traversable wormholes, potential gateways through time, could serve as a mechanism for time travel. However, the energy needed to create and sustain a wormhole would be astronomical. Estimates suggest it might require negative energy or exotic matter, which defies the known laws of physics. Even if such materials existed, generating enough negative energy to keep a wormhole stable would be far beyond the capabilities of any technology humanity currently possesses. Stability issues further complicate the picture. Wormholes, if they could be created, are inherently unstable structures that would likely collapse before anything could pass through them. Kip Thorne and his colleagues have theorized that stabilizing a wormhole might be possible with exotic matter, but even this remains speculative. Without exotic matter, the gravitational forces at the throat of a wormhole would cause it to pinch off, rendering it unusable. Moreover, introducing a traveler or even light through a wormhole might destabilize it further, potentially causing catastrophic collapse. Adding to these challenges is the lack of experimental evidence. While Einstein's theories and subsequent experiments have provided tantalizing hints of time dilation and space-time curvature, no empirical data supports the existence of wormholes or other mechanisms necessary for time travel. Efforts to simulate these phenomena in controlled settings, such as particle accelerators, have yet to yield conclusive results. Theoretical models remain just that, theoretical, until technology advances enough to test them. These scientific hurdles illustrate the vast gap between theory and application. While the mathematics of time travel may hold up under scrutiny, translating those equations into functioning mechanisms remains a monumental task. It is a reminder that even the most imaginative ideas must eventually contend with the physical limits of the universe. Ethical and philosophical questions beyond the scientific challenges, time travel raises profound ethical and philosophical dilemmas. The potential to alter the past or influence the future brings with it a cascade of unintended consequences. For instance, if a time traveler were to change even a minor event in the past, the ripple effects could fundamentally alter the course of history. This concept, often dramatized in science fiction as the butterfly effect, underscores the inherent unpredictability of tampering with time. Could a seemingly trivial action, such as stepping on an insect in the past, lead to a vastly different present? Such scenarios highlight the risks of disrupting the delicate balance of causality. Even if time travel were possible, should humans have the right to use it? The morality of revisiting historical events poses significant questions. On one hand, the ability to witness or even prevent tragedies, such as wars or genocides, might seem like a moral imperative. On the other hand, interfering in the past could create new conflicts or erase the progress that emerged from those events. Would preventing a war, for example, also erase the technological advancements or societal shifts that arose in its aftermath? These dilemmas force us to confront the limits of human responsibility and foresight. Another ethical question involves the potential misuse of time travel for personal or political gain. Would individuals or governments use it to consolidate power or rewrite history in their favor? The very existence of such a capability could destabilize global systems, creating a new kind of arms race where control over time itself becomes the ultimate weapon. These philosophical and ethical challenges remind us that time travel is not just a scientific endeavor but a moral one. It forces humanity to confront questions about our collective values, responsibilities, and the consequences of our actions across time. Government and military interest. The allure of time travel has not been confined to scientists and philosophers. Governments and military organizations have also expressed interest in its potential applications. Alleged secret experiments, such as the Philadelphia experiment and the Montauk project, have fueled speculation about covert attempts to manipulate time. While many of these stories remain unverified and often dismissed as conspiracy theories, they highlight the perception of time travel as a tool for strategic advantage. The Philadelphia experiment, for instance, is an infamous tale claiming that the US Navy attempted to render a warship invisible during World War II. According to the legend, the experiment inadvertently caused the ship to travel through time, with disastrous consequences for its crew. While no credible evidence supports this story, it has persisted in popular culture, symbolizing the potential dangers of tampering with time. Similarly, the Montauk project alleges that the US government conducted experiments in the 1980s involving time travel, teleportation, and mind control. These claims, though widely regarded as fiction, reflect public fascination with the idea that time travel could be weaponized for military or intelligence purposes. Even without direct evidence, the speculative nature of these stories points to the potential risks associated with time travel technology falling into the wrong hands. If time travel were to become a reality, its misuse for political or military gain would pose a significant threat to global stability. Imagine a world where nations could alter historical events to weaken rivals or secure resources, creating an unbalanced and unpredictable geopolitical landscape. Such scenarios underscore the need for international cooperation and regulation should time travel ever move beyond the realm of theory. Government interest in time travel also raises concerns about secrecy and accountability. Would such technology be accessible to all, or would it remain in the hands of a few powerful entities? The prospect of a select group controlling time travel creates ethical and political dilemmas, as it could widen existing inequalities and give unprecedented power to those in control. While much of the speculation about government involvement in time travel remains in the realm of conspiracy theories, it highlights the broader concerns about how such a capability could be used, or abused. Whether as a tool for exploration or a weapon of control, time travel poses challenges that extend far beyond science, requiring careful consideration of its ethical, political, and societal implications. Are we closer today? Today, the idea of time travel is no longer confined to science fiction or theoretical debates. It has become an active area of scientific inquiry. Around the globe, researchers and institutions are exploring the boundaries of physics, searching for evidence and mechanisms that could one day make time travel a reality. Among the most notable contributors to this field are theoretical physicists like Thorne and quantum researchers delving into the nature of space-time. One promising avenue lies in the study of quantum mechanics, particularly the use of quantum computers. These revolutionary devices, which harness the principles of quantum superposition and entanglement, are already transforming fields like cryptography and materials science. Their potential role in time travel research stems from their ability to simulate complex systems, including the behavior of particles in extreme environments. Quantum simulations might offer insights into how space-time behaves near wormholes or black holes, where time manipulation could theoretically occur. Another cutting-edge concept involves quantum entanglement, often referred to as spooky action at a distance, by Einstein. Recent experiments have shown that entangled particles can instantaneously affect one another, regardless of the distance between them. Some theorists propose that understanding this phenomenon could pave the way for transmitting information, or even matter, through time. Institutions like the Perimeter Institute for Theoretical Physics in Canada and the Max Planck Institute for Gravitational Physics in Germany are at the forefront of these efforts, exploring the mathematical and experimental frameworks required for time travel. Additionally, independent researchers like Ronald Mallett continue to push the boundaries, proposing innovative concepts such as laser-based time loops. While these ideas remain theoretical, they underscore the growing scientific interest in this once taboo topic. Global collaboration in time travel research is not the endeavor of isolated scientists. It is a collaborative, global effort. Organizations like CERN, home to the Large Hadron Collider, LHC, play a pivotal role in advancing our understanding of space-time. By colliding particles at nearly the speed of light, the LHC recreates conditions that existed moments after the Big Bang. These experiments allow scientists to study fundamental forces and particles that could reveal new insights into the nature of time. For example, the detection of the Higgs boson in 2012 marked a significant milestone in understanding the universe's building blocks. Some theorists speculate that further discoveries at CERN could include exotic particles or phenomena that hint at time travel possibilities. Researchers are particularly interested in tachyons and closed time-like curves, which could theoretically enable travel through time. International funding for space-time research has also increased, with countries like the United States, China, and European nations investing in advanced physics projects. NASA's continued exploration of black holes, through missions like the Event Horizon Telescope, contributes valuable data that may one day inform time travel theories. Similarly, space agencies like the European Space Agency, ESA, and Roscosmos collaborate on gravitational wave detection and other projects that deepen our understanding of space-time. These collaborations demonstrate that time travel is not just a speculative dream but a topic worthy of serious scientific exploration. The pooling of resources and expertise from around the world accelerates progress, bringing humanity closer to answering the question of whether time travel is possible. Predictions for the future. How close are we to achieving time travel? According to experts, it depends on the type of time travel in question. Moving forward in time is already possible, at least on a microscopic scale. Astronauts aboard the International Space Station experience time slightly slower than those on Earth due to relativistic effects, effectively traveling fractions of a second into the future. However, traveling backward in time or creating large-scale time loops remains far more elusive. Prominent physicists like Stephen Hawking have expressed skepticism about backward time travel, citing paradoxes and the lack of experimental evidence. However, others, like Kip Thorne, remain cautiously optimistic, arguing that the mathematics behind wormholes and closed time-like curves is sound. Thorne suggests that advances in energy generation and material science might one day make these mechanisms feasible. The timeline for practical time travel depends heavily on technological breakthroughs. Experts predict that advancements in quantum computing, energy manipulation, and exotic matter production could pave the way for experimental demonstrations within the next century. However, achieving human-scale time travel could take several centuries or more, given the immense challenges involved. To move closer to time travel, humanity must focus on incremental steps. Developing better particle accelerators, exploring quantum phenomena more deeply, and improving our understanding of black holes are all critical. Additionally, fostering international collaboration and increasing funding for theoretical physics research will be essential. While the journey is long, the progress made in recent decades suggests that time travel is no longer an impossible dream but a distant possibility. Case study. Prominent physicists offer diverse perspectives on the feasibility of time travel, each contributing unique insights to the discussion. Ronald Mallett, for example, has proposed using rotating laser beams to create a closed time-like curve. While his ideas are controversial, they highlight the potential of using light and energy to manipulate space-time. Mallett's work serves as a reminder that time travel research is not limited to large institutions but can also emerge from individual creativity. Kip Thorne's contributions to the study of wormholes have been equally influential. Thorne's mathematical models suggest that wormholes, if stabilized with exotic matter, could function as time machines. His collaboration with filmmakers on Interstellar helped popularize these ideas, bringing complex physics to a global audience. NASA and other space agencies also provide valuable contributions to time travel research. Missions like the James Webb Space Telescope and gravitational wave detectors allow scientists to study space-time in unprecedented detail. Observations of black holes and other extreme environments offer clues about how time behaves under intense gravitational forces. These case studies demonstrate the multifaceted nature of time travel research, combining theoretical work, experimental exploration, and public engagement. By examining the efforts of individual scientists, global institutions, and space agencies, we gain a clearer picture of how humanity is progressing toward unraveling the mysteries of time. The journey is far from over, but the strides made today lay the foundation for the breakthroughs of tomorrow. The impact of time travel on society. The advent of time travel would represent a seismic shift in human society, fundamentally altering science, education, technology, and even daily life. Imagine a world where scientists could directly observe historical events instead of relying on fossils or artifacts. The ability to study ancient ecosystems, witness the extinction of the dinosaurs, or observe early human civilizations would revolutionize fields like anthropology, geology, and evolutionary biology. Time travel could also offer unprecedented insights into the universe's origins, providing direct evidence of events like the Big Bang. In education, time travel could become the ultimate teaching tool. Students could immerse themselves in historical events, from walking the streets of ancient Rome to witnessing the signing of the Declaration of Independence. Such experiential learning could transform the way people understand history and culture, fostering a deeper appreciation of humanity's shared past. Beyond history, time travel could accelerate technological progress by allowing researchers to bring back advanced knowledge from the future. However, this raises ethical concerns about how such advancements would be used and whether humanity would be ready for them. On the societal level, time travel would undoubtedly create challenges, particularly around access and equity. If time travel technology were controlled by a select few, governments, corporations, or the wealthy, it could exacerbate existing inequalities. A scenario where only the privileged could afford to travel through time might deepen class divides, creating a new form of societal stratification. Access to time travel could also become a geopolitical issue, with nations vying for control over the technology to gain strategic advantages. These challenges would require careful regulation and international cooperation to ensure time travel benefits humanity as a whole rather than serving as a tool for exploitation. Theories about time travelers today. Speculation about time travel is not confined to the future. It permeates the present, with countless stories and alleged sightings of time travelers. These tales often blend intrigue and skepticism, capturing the public's imagination while inviting scientific scrutiny. One famous story is that of John Titor, an individual who appeared in internet forums in the early 2000s, claiming to be a time traveler from the year 2036. Titor shared detailed accounts of his supposed mission to retrieve an IBM 5100 computer to solve a computational crisis in the future. While most experts dismissed Titor's claims as a hoax, the story became a cultural phenomenon, sparking debates about the plausibility of time travel and its potential societal implications. Other alleged time travelers have surfaced in photographs and videos, with claims of modern objects appearing in historical contexts. For instance, a widely circulated image shows a man at a 1941 bridge opening ceremony wearing what looks like contemporary sunglasses and a printed t-shirt, earning him the nickname time-traveling hipster. While experts attribute such anomalies to coincidence or misinterpretation, these cases highlight how the idea of time travel continues to captivate the public. Conspiracy theories about time travel often intersect with claims of government cover-ups. Stories like the Philadelphia experiment and the Montauk project suggest that time travel experiments have already occurred but remain hidden from the public. While these theories lack scientific evidence, they shape perceptions of time travel as both a possibility and a secret endeavor. These narratives reflect society's fascination with the unknown and the human desire to believe in extraordinary possibilities. Whether rooted in science or speculation, stories of time travelers serve as a reminder of how deeply time travel resonates with the collective imagination. Philosophical reflection. Time travel doesn't just challenge our understanding of physics, it redefines humanity's place in the universe and our perception of existence itself. At its core, time travel forces us to grapple with profound questions about free will, causality, and the nature of time. If the past can be revisited and the future explored, does that mean our lives are predestined, or can we still shape our destinies? The concept of time travel also raises questions about the meaning of history. If events can be altered or observed through time travel, do they lose their significance? Would humanity still feel the same sense of progress or collective identity if the past were accessible and malleable? These questions challenge the linear narrative of history, offering a more fluid and interconnected view of time. Moreover, time travel could reshape humanity's understanding of morality and responsibility. With the power to alter events, individuals and societies would face unprecedented ethical dilemmas. Should we intervene in historical atrocities or allow them to stand as warnings for future generations? How would humanity reconcile the potential for good with the risk of unintended consequences? These questions force us to reconsider our values and the impact of our actions across time. On a broader scale, time travel offers a unique lens through which to explore existence itself. The possibility of observing the universe's beginnings or witnessing its distant future might provide answers to some of humanity's greatest questions. Where did we come from? What is our purpose? What lies ahead? Time travel could expand the scope of human inquiry, transforming our understanding of reality and our place within it. Ultimately, time travel is more than a scientific or technological achievement, it is a philosophical frontier. Its implications reach far beyond physics, touching every aspect of human existence, from how we view ourselves to how we shape the world. In this sense, time travel is not just about exploring the past or future but about reimagining what it means to be human. Time travel, long considered a fantasy of science fiction, is now a subject of serious scientific inquiry, blending the boundaries of imagination and reality. From Einstein's theory of relativity, which redefined time as a flexible dimension, to modern experiments in quantum mechanics and gravitational physics, humanity has made significant strides in understanding the nature of time. Breakthroughs such as the detection of time dilation and theoretical studies of wormholes and closed time-like curves suggest that time travel, at least forward in time, is scientifically plausible. Yet, the challenges are monumental. The energy requirements for stabilizing wormholes, the lack of exotic matter, and the absence of empirical evidence remain formidable obstacles. Beyond the technical hurdles, time travel also poses profound ethical and societal dilemmas. Questions about altering history, the morality of revisiting the past, and the potential for misuse highlight the need for caution and regulation. Meanwhile, stories of alleged time travelers and conspiracy theories keep the topic firmly rooted in popular culture, reflecting society's enduring fascination with the possibility. The societal impact of time travel, should it ever become a reality, would be transformative. It could revolutionize science, education, and technology while also introducing new challenges related to equity and governance. As humanity explores the feasibility of time travel, these questions will continue to shape the discussion, blending scientific ambition with philosophical reflection. The allure of time travel lies in its dual nature, equal parts hope and mystery. It is a concept that captivates the imagination, offering a window into the past and a glimpse of the future. For centuries, humans have dreamed of revisiting defining moments, undoing mistakes, and exploring what lies ahead. This fascination reflects a deeper longing to understand time itself, a force that governs every aspect of existence yet remains elusive and enigmatic. While the scientific pursuit of time travel is filled with skepticism and uncertainty, it is also driven by the same relentless curiosity that has propelled humanity toward other great discoveries. From the first steps on the moon to the decoding of the human genome, science often begins with dreams that seem impossible. Time travel may be one of those dreams, an aspiration that pushes the boundaries of what we know and challenges us to think beyond the confines of the present. The pursuit of time travel, even if it remains theoretical, holds value in its capacity to inspire. It encourages us to ask questions about existence, causality, and the universe's mysteries. It reminds us that progress often lies at the intersection of imagination and inquiry, where bold ideas spark the next wave of discovery. The exploration of time travel is not just the domain of physicists and theorists, it belongs to all of us. By engaging with scientific research, supporting advancements in technology, and fostering critical thinking, we can contribute to the understanding of time and its possibilities. Time travel may not yet be within our reach, but the journey to explore it is a testament to human ingenuity and our unyielding curiosity about the universe. As you reflect on the ideas presented in this video, consider this: if time travel were possible, would you use it? What moment in history would you visit, or what future would you explore? Share your thoughts in the comments below and join the conversation. Whether or not we ever unlock the mysteries of time travel, the journey of exploring it is one of humanity's most profound adventures. Let's continue to dream, question, and discover together.